All right, so let me go ahead and get started. I just want to make a few final comments about sort of the part 2 of the class, and then we're going to move on to part 3. So where are we? So we've been striving for these 3 things. We've been looking for strong incentive guarantees so far, DSIC or EPIC back in part 1, welfare, optimal or almost optimal, and polytime mechanisms. And up to this point in the class, we constrained ourselves to these super strong incentive guarantees. We could get away with it in part 1 because I sort of shepherded you through tractable special cases where we could get everything we want. And we just finished a couple weeks though where of NP hard special cases of welfare maximization. And what we discovered is that just already 2 and 3 jointly is non-trivial. It's NP hard, so you're looking for approximation algorithms, but at least there's a lot of tools there, a lot of positive results known. But then if you add in DSIC on top of it, things get actually quite difficult indeed, in 2 senses. So first of all, the positive results that are known, you have to work quite hard to get those positive results, and complex mechanisms seem required to get them. And then secondly, and this is what I'll comment on at the moment, is there's lots of cases where it's just simply impossible. Okay, so no matter how hard you work, no matter how complex your mechanism, you can't get all 3 of these properties simultaneously. So yeah, so let me just comment on some negative results. So scenario number 8, this was what motivated us throughout part 2. This was bit with submodular valuations. So this was just a little bit beyond gross substitutes, but already welfare maximization was NP hard. And part 2 culminated with a positive result last week. We showed that for a special case of submodular valuations, namely these coverage valuations, we gave a DSIC mechanism that was very good. That was 63% of the optimal welfare, and that's actually best possible, even ignoring incentives, unless P is different than NP. But what about sort of the general version of scenario 8? Okay, so what about full-blown submodular valuations without this coverage restriction? And let's say I give you black box access just through value oracles, and that's all we needed. All we were using was value oracles with the coverage valuations. So with just 2 and 3 jointly, the news is good, okay? So there's a beautiful algorithm by Vondrak, which those of you who just sort of like combinatorial optimization, I recommend reading this sometime. It's really a very nice algorithm. And so this says ignoring incentives, you can get 1 minus 1 over E for submodular valuations only using a polynomial number of value queries. Okay? So this says there's at least no obstruction to a complete solution for scenario 8 just from parts 2 and 3. So the question is, what happens when you add in DSIC also? And it turns out we now understand that the problem is just fundamentally much, much, much harder. If I insist that you solve the problem using a DSIC mechanism. So the first, so basically a pair of papers by Doug Zinsmy and Dugme and Vondrak basically show that non-trivial, I'm not going to state the formal version, but non-trivial approximation. Or here non-trivial means anything better than a polynomial approximation factor. So we're talking just beating something really terrible like root m, where m is the number of items. So forget about 63%. I mean just anything, certainly any constant, no matter how small, requires an exponential number of value queries. Okay, so this is DSIC. And this is even if it's just what's called a truthful and expectation mechanism. So it's not just for deterministic. The first results for deterministic and some bells and whistles on them. And then the second paper shows that even with the full-blown MIDR mechanisms, you can't do better. You can't get non-trivial approximation with less than exponentially many value queries. Okay? And this, despite being sort of bad news, just intellectually, this is a real kind of triumph of this algorithmic game theory field, actually. So, and a lot of these results have only been the last 5 years or so. We now understand, in a rigorous sense, how incentives make NP hard problems much, much, much harder than if you just care about approximation algorithms. Okay? So I'm not going to talk about this now. I think especially this first paper would be a good topic for a bonus lecture. So maybe in a couple weeks, if there's interest, we can talk about it. It's a doable argument. So instead, what I want to do now is plunge on to step 3, where we say, let's relax this. So let me just write something weaker here. and with the hopes of getting sort of two benefits. First of all, just that these negative results, we want them to go away, and they will go away, so we'll get much more sweeping positive results. Also, the mechanisms will get simpler, generally speaking. Okay? So the incentive guarantees won't be as strong, but there'll be lots of other benefits. Oh, one other thing I want to mention here. So sort of a really kind of nice open question is if you have demand queries. So let me just jog your memory. What are all these queries? So in general, if you have a valuation, value query just says you ask it for a set and it tells you back what the value of that set is. Kind of any reasonable model evaluations, you can implement value queries in polynomial time. Demand queries, while they're useful and natural in an auction context, it sort of depends. We've actually seen some examples where demand queries are NP hard, including coverage valuations that we talked about last week. But sometimes you can implement these in polynomial time, and when you can do useful things with them. And the main application you saw of demand queries was when we solved the LP relaxation of the welfare maximization problem. How did we solve it? We passed to the dual. The separation oracle for ellipsoid in the dual was a demand query. So that's what we needed to solve that linear programming relaxation, and we've used that in a couple different contexts. Okay? So it's known that you actually, with demand queries, and in a DSIC mechanism can get a non-trivial approximation, although it's basically logarithmic in the number of goods, and we don't know whether a constant factor is possible or not. Okay, so that's sort of a major open question sort of in this part of the world. Can you get a constant factor DSIC mechanism with demand queries? You cannot with just value queries. Okay? All right. So on to part 3. So we're going to compromise on the incentive guarantee. And the question now is, what compromises could we make? What would be a sensible weakening of dominant strategy incentive compatibility? So the main answer to that is something called is Bayesian incentive compatibility. Okay, and so that's what, I'm not going to talk about that in this first lecture, but we'll talk about it a bit toward the end of the day, and quite a bit for the rest of the class. And that's where we're going to have a common prior, and basically we're going to ask that all the bidders are optimizing an expectation over this prior. And that's sort of a very traditional approach to mechanism design. Before we get to these Bayesian incentive compatible mechanisms, I want to take a detour. I want to show you one result, which at this point is sort of a curiosity in the literature. So the incentive guarantee will be weaker than DSIC. Bidders will not have dominant strategies in the auctions I will show you, but it will still very much have the spirit of DSIC. We have to make very minimal behavioral assumptions to argue that we get what we want from this mechanism. And I'll be precise about that. But this sort of notion of a little bit weaker than DSIC, basically players not playing stupid strategies, there's not a lot known either on the positive side or the negative side. I'm going to show you kind of the main positive result known. We don't really know anything negative, so again, this seems like a very interesting direction for more research. Okay? So next, so this will be all of the first lecture today, and I might spill over after the break a little bit also. So DSIC, the only behavioral assumption was that if a player has a dominant strategy, they play it. Now, so a foolproof strategy, players will play. Now we're just going to assume that if there are stupid strategies, bidders don't play the stupid strategies. Okay, stupid meaning it's dominated, sort of obviously dominated by something else. Okay. So assume bidders don't play stupid strategies. Okay, and I'm not, in the context of the concrete mechanism, it'll be very clear what I mean by this. Okay, it'll be very clear what I'm assuming. All right, so any questions before I start sort of talking to you about the setting and the mechanism where we look at this relaxation of DSIC? Okay. All right, so this is going to be another scenario, but not very different than some of the other ones we've seen. So this is going to be called single value multi-minded bidders. So let me say what I mean. So we again have our set of non-identical goods. And each bidder I, we don't know what it wants. But we know there's some bundles of goods that it wants. Okay? So the simplest case would be sort of unit demand. We know it wants, a singleton good, and it doesn't care which singleton it gets. Or maybe it wants a pair, and we don't know which pair. Okay? So there are these things these bundles that it wants. Okay? So could be one, could be many, we don't know. And then a strong assumption, okay, but one that's important for the results I'll say, is a valuation VI, and VI is the same for all of the bundles, okay? So it's in the spirit of unit demand in that the bidder doesn't want many of these, it only wants one. And as soon as it gets one of these bundles, it gets a value of VI, okay? So again, a very simple case would be the bundles are just the singletons of U. That just says I want one good. To me, they're all the same. I don't care which I get. It's worth $5, okay? Okay. So formally, given this information, the valuation for bidder I is just defined as VI if S includes one of these desired bundles, some AIL, and 0 otherwise. Okay? So it's single value, because there's the same value for every bundle, and it's multi-minded because it wants, these are the the bundles it might want. All right, so what are some other examples? So, one example, you could imagine that you have a network, and as a bidder, you have some source and some sink in this network, and those are private. The seller doesn't know what they are. And then what you want is just a path from your source to your destination. Okay? And so then here goods correspond to edges, and the bundles correspond to the path from your source to your destination. If the seller doesn't know your source and destination, it doesn't know your bundles. And you don't care, and then this assumes you don't care which path you get, you just want some path. Another example, you could imagine you're a firm and you just want some task to get done. VI is sort of the value for getting this task done. And you need some workers that have enough skills that are needed for the task. Okay? And so maybe sometimes 3 workers are good enough to accomplish this task. Maybe if you get some really good workers, 2 of the workers are good enough for this task. And you don't care which ones you get, just as long as the task can be achieved. Okay? So those would be some examples where you might see this. Questions about that? So let me develop your intuition by mentioning 2 special cases that can be solved by DSIC mechanisms. And you may have even done these on homework last quarter. I don't actually remember. So special case number 1 is if I also tell you what these bundles are. So special case number 1, AILs, all publicly known. So in other words, you know what bidder I wants, you just don't know how much they're willing to pay for it. You don't know VI. That's the only thing which is still private. Okay? So these are the kind of problems that we talked about some last quarter. Okay? This is a single parameter problem now. From a bidder's perspective, either they get a bundle they want or they don't get a bundle they want, and they have this private value, and that's sort of like winning, and they have this private value VI for winning. Okay, so this is where we have Meyerson's lemma that says, allocation rules can be turned into DSIC mechanisms if and only if the allocation rule is monotone, meaning the more you bid holding everyone else fixed, the more likely you are to win. Or you only switch from losing to winning, never the reverse, if you raise your bid. Okay, so this is a single parameter problem. And one of the things we talked about last quarter is how greedy algorithms often give monotone allocation rules and therefore lead to DSIC mechanisms. And that's equally true here. So greedy gives a DSIC. Oh, there's one parameter I forgot to tell you about. So we're going to assume that all desired bundles have cardinality at most D. Okay? And D is known to the seller. So you might want to think of like D is maybe 6. And then, the bundles have sizes 1, 2, 3, or 4, something like this. Okay? Okay. So greedy gives a DSIC 1 over D approximation. So let me tell you what I mean by greedy. So what I mean by greedy is you just sort the bidders so you get people's reported valuations. You sort them from high to low. Okay, you start with the highest bidder. You give them one of their bundles. Okay? You go to the next highest bidder. You look at the bundles they want. If any of them don't conflict with goods you've already allocated, you give them one of them, and so on. And you just go through the bundles in this way, allocating people a bundle if you can. All right? So that's going to be monotone, because as you raise your bid, you go only earlier in this ordering. Okay? So if you get allocated later, you're going to get allocated earlier as well by greedy. Now, this is not an optimal algorithm. Okay, it doesn't maximize welfare, but it loses a factor D. Okay, and I'll leave the proof as an optional exercise, but the intuition, I hope, is very clear. So you give someone a bundle and it has at most D items. Okay, so how could you have screwed up by giving these D items to this bidder? Well, maybe by giving this bidder those D items, you blocked these D other bidders in the optimum that you really wish you had allocated instead. Okay? But you're running a greedy algorithm, so those D bidders' values is at most as much as the one you're just getting credit for now. So you get once times a value instead of D times a value. So that's the 1 over D. Okay? And it turns out, so this is an NP-hard problem, so even in this public bundle case, and it's not trivial to approximately maximize welfare. In fact, you can't do much better than D. Okay, so there's a reduction from independent set and bounded degree graphs that shows basically, 1 over D is what you're stuck with, and greedy already gives it to you. Okay? So this special case, we kind of, subject to P versus NP, worst case approximation, we know what to do with it. Okay, you just run greedy. And this will be relevant for the mechanism that I show you. Okay? All right, so special case number 2. All right, and can't do much better. So special case number 2 is when each bidder has only one bundle. Okay, so when each bidder has only one AI. So that's called single-minded bidders. But in this case, so it's incomparable to special case number 1 in the sense that over here, you don't know what the bundle is. Okay? So only one unknown bundle per bidder. Okay? So this now is not a single parameter problem, right? Because there's 2 things you don't know about a bidder. You don't know its value VI, and you don't know the bundle it wants AI. Okay? So like Meyerson's lemma, for example, doesn't apply automatically. Okay? But it turns out greedy still gives a DSIC 1 over D approximation. Okay, so what do I mean by greedy? Well, so now you have to ask people for 2 things, not just one thing. Right? Before we asked them just for their value, now we say, what's your value and what's your set? And now you run the same algorithm you did before. Okay, you just sort them from high to low by reported values, and you just greedily give them a set if you can. Okay? So it's definitely a 1 over D approximation if it's DSIC, because it's sort of a special case of the previous algorithm. And you can sort of prove just from scratch that it's DSIC, basically. It's sort of close enough to a single parameter problem, you can just prove that it works. Intuitively, from a bidder's perspective, given that it only wants this one set, it's never going to report a set that excludes any of the items that it wants, because then it's guaranteed 0 utility. And by enlarging the set, you only make it more likely that you're not going to be feasible when the greedy algorithm gets to you. So there's not really any reason to lie about the set. And then once you're not lying about the set, it basically defaults back to the single parameter analysis. Okay? So again, I'll leave the details as an optional exercise, but that's kind of the idea of why this is also DSIC here. Okay? All right. So in this sense, scenario number 9 is kind of just a little bit, beyond what we know how to do with DSIC mechanisms. And we'll show how basically, taking this greedy basically an indirect implementation of this greedy algorithm with a couple twists is good enough to get, okay, it won't be 1 over D, but it'll be 1 over D plus some other factors. And it won't quite be DSIC, but it'll be close to DSIC. Okay? And again, I'm going to present this to you not as something like, that's, from the book of magical proofs, although it's not that complicated, it's pretty nice, but more just sort of as an intriguing, point that, it feels like there should be some broader theory around. Okay? Okay. So any questions? Everyone clear on the scenario? So now we're going to go back to the full-blown scenario. Again, there's only one private value. All your bundles are worth this, but you have a unlimited, in effect, number of bundles. All cardinality most D that you might want, and you're happy to get any of them. Okay? All right. All right, so let me tell you about what I'm going to call the shrinking mechanism. And so this is due to Babayev, Levy, and Pavlov from '06. So it's been around. Decent number of people know about it. It's sort of no one's really known how to build around this. Okay. All right. So it's going to be an indirect mechanism. Okay. I thought we were done with indirect mechanisms, but we were going to see at least one more. This one. So we're never even going to really ask bidders what bundles they want explicitly. We're going to sort of force them to choose as the auction proceeds. So we're not going to actually ask them for their value either. It's going to have sort of an ascending auction flavor on the values. So I should say, let's assume. So we're also going to assume that all values are at least, let's say, 1. Really, the assumption is you know some lower bound on people's values. Okay, call it 1. So you initialize the bids to be the lowest the values could be. These will only go up over the course of the auction. Okay? So just like an ascending auction, we're going to systematically ask bidders, are they happy with us increasing their bid on their behalf? Or do they want to drop out? Then there's going to be the goods that a bidder is after. Okay, so we're going to force a bidder to kind of narrow its focus as the auction proceeds. Okay? So initially there's no restrictions. So SI is the items which are still permitted to be allocated to bidder I. Anything outside of S sub I cannot get, no matter what. Okay? So this will only be decreasing as the auction proceeds. Okay? And then I'll need a couple sets of bidders just to keep track of stuff. So let me just put these here. Okay, so losers is going to be the bidders that have dropped out irrevocably from the auction forevermore. Okay. So let me show you the main loop, and then we'll do an example. So while there are bidders which sort of have neither dropped out nor won in the previous iteration of the auction, we're going to compute a new candidate allocation. Okay, so new is going to be what we're computing in this iteration of the while loop. And the way I want you to think about what we're about to do next is I want you to remember what we said about the greedy algorithm. Okay? In some sense, what we're doing is reducing the known case to the unknown case. Okay, meaning the known bundles case to the unknown bundles case, relaxing the incentive guarantee a little bit. So if we knew all of the bundles, and we were happy getting a D approximation, we would sort bidders by value, high to low, and we just allocate them a bundle as long as we can. Okay? So the problem, of course, being is that we don't know the bundles, right? So we can't do this. So we're going to ask the bidders to kind of help us simulate this greedy algorithm, okay? Because they know what bundles they want. Notice that in the greedy algorithm, the order in which we go through the bidders is independent of the bundles. Right, so in the greedy algorithm, we go through the bidders from highest value to lowest value. We don't even need to know the bundles to know the ordering, okay? But we do need to know the bundles to know who to allocate and to what. So now we go through all the bidders that haven't dropped out yet. So go through all bidders I, and remember, losers are the ones that have dropped out forever. We don't know the values, but we have these lower bounds, these presumably lower bounds, these proxies, these BIs. From high to low bid, break ties canonically, for example, lexicographically. Okay. So we want to run the greedy algorithm, okay? And right, so basically new is what we're computing. So you should think of this as being the greedy, the output of the greedy algorithm that we're computing one at a time right now. So intuitively what we want to say is that, when we get to a bidder I, if it doesn't conflict with people we've already allocated, then we should go ahead and add this bidder to new, okay, to the allocation we're computing. Was there a question? Yeah. There's one annoying twist, though, actually, which is in this greedy algorithm. So there's this one thing that's kind of weird, all right, which just adds a little wrinkles to the analysis, which is at the end of the day, think of U as being like 100 goods. Okay, so there's lots of items, and think of D as being maybe 6 or 10. Remember, that's sort of an upper bound on the cardinality of goods that anyone wants. All right, and D is pretty important, right? Because like in the greedy algorithm, D is what shows up in the approximation ratio. So we're thinking of D being small, right? Now, when we initialize this mechanism, on the other hand, we basically say, a bidder is essentially going for everything, going for all 100 items, right? So this is way, way bigger than D in the case we're thinking about. So, and there's going to be this annoyance where there'll just be, from a bidder's perspective, there'll be this kind of initial phase where it hasn't given you any information about what items it's targeting. As far as you know, it wants any of the 100 goods. And then there'll be this first phase where we force it to target at most D items, okay? So the relevant twist right now is that, we don't want to run the greedy algorithm with any bidders that have, sets of 100 items. We want them to be at most D. So here's the twist. We say if, so again, remember, SI are the items that I might conceivably get. Anything outside SI, I is definitely never going to get. And this is what's shrinking over the course of the auction. So if I has narrowed its focus to at most D goods, okay, this sort of makes it eligible for the greedy algorithm. And SI feasible for new, meaning whatever other bidders that have been added to new, their SIs are disjoint from this one. Then we add I to new. Okay. So that's just that's an iteration of the greedy algorithm that's successful, where we can add this person, there's no conflict. Now here's what's sort of cute. So if it's the case that the greedy algorithm normally in this iteration would take a pass, because we're at this bidder I and it has these set items SI it might get and it conflicts with people we've already taken in new, we give the bidder the opportunity to shrink the items that it wants at this point. Okay? So if bidder I's bundle S sub I, its items S sub I conflicts with new, we say, well, if you want, you have the option to shrink SI to TI. So in other words, we ask the bidder to volunteer some of the items in S sub I and agree to, that it will be excluded from getting allocated those at any point for the rest of the auction. Okay? So TI is what's left, where, okay, so TI should be at most D, and TI feasible for new. Okay? So think of this as saying, like we go up to bidder I and we're like, look, based on the commitments we've already made in this iteration, we're going to take a pass on you. Okay? But here are the items that are sold. Here are the items that have been sold. Here are the ones that are left. Okay? Some of the ones that have been sold are in your SI. If you want, you can suggest a strict subset of your SI, TI, which consists only of items we haven't sold yet. And if you do that, and there's at most D items, then all of a sudden you're eligible for the greedy algorithm, and we'll go ahead and pick you and add you to new. Okay? But it's up to you. You don't have to do that, but you can if you want. So in particular, this is the first time, just from a bidder's perspective, right? So even like the highest bidder at the beginning of the algorithm is going to be asked this question, right? Because again, think of this as like 100 items and D is like 10. If you're the highest, initially all the bids are 1, so it's the highest bidder. So let's just say the bidder with the alphabetically first name. First iteration of the while loop, first iteration of this loop, basically that first bidder is going to say, look, your S sub I is bigger than D, so we're going to skip you. Or, but if you want, suggest a subset of size at most D, and then we'll pick you. Okay? So that's the first shrinking by a given bidder. Okay. So if the bidder agrees, then we reset the items it might conceivably get to this shrinked set TI. And then, again, simulating the greedy algorithm, we add I to the allocation new. Okay? Option 2 is you just pass. You can say, no, I think I'll just stick with S sub I. Thank you very much. Okay. So we're not done, but that's one of the 2 questions that we ask bidders in a given iteration. All right. So let me actually, let me skip a step, which is less important. Let me tell you about the other thing that, let me try to motivate, the incentives that face a bidder when they're trying to decide which of these 2 options to take. Okay? So the point is, like, if you don't shrink your, I mean, the way I've written it, kind of is like, why would you ever shrink your set? What's the benefit? Okay, so let me explain that. So basically the next thing happens for a bidder, so basically for anybody not chosen, okay, so for anyone not chosen by the greedy algorithm, they're going to be asked again one of 2 things. They say if you weren't chosen by the greedy algorithm, then you either have to drop out or double your bid. Okay? You wanted these items, you didn't get them. We need to make progress. Either your values, right? So remember, we don't know people's values. We just have these sort of doubling estimates, these lower bounds on people's values. So if we didn't allocate to this person, we need some information, right? Either our estimate of their value is too low, right? They have this really high value, and they should be allocated. And so we say, okay, then double your bid. Put your money where your mouth is. Double your bid, and you'll have a better chance next time being chosen in the greedy algorithm. Or drop out. Okay, sorry, there's just too much competition. You're not going to win. Okay. So option 1 is losers double their bid. Option 2 is I can drop out, in which case we add I to the losers. Okay? So again, there's an interplay between these 2 options, right? Okay, so to first order, as you'll see, this isn't going to be quite true, but the way you should think about it is, in this basically what a bidder is deciding between, okay, so the happy case is when greedy just picks you and you don't have to do anything. Okay, that's awesome, because you're not competing with other bidders or your bid is just so high. Then you're happy. So the problem is, what if you're not going to get chosen by the greedy algorithm? This auction gives the bidder 2 ways of succeeding in the next iteration. And they're really pretty different ways, actually. The first way is you bid higher, okay, and then you go earlier in the greedy ordering, so you have a better chance of getting your items S sub I. Or you're allowed to just go after fewer items, shrink your set, and you'll have fewer conflicts with other bidders. Okay? So either your bid stays the same and your set shrinks, or your set stays the same and your bid doubles. Okay? So those are that's the trade-off you're facing as a bidder. And there's not going to be a dominant strategy. Okay? And that's kind of what's really interesting about this auction. Like as a bidder, it's not really obvious what you should do. It's going to be obvious things that you shouldn't do, and the guarantee for the auction will hold as long as bidders don't do obviously stupid things. But it's not like we're going to have some prediction about what happens in the auction, like with truthful mechanisms where we just expect people to just do direct revelation. So that's sort of what's quite different about this auction. Okay, let me fill in the details though. So there's this other piece, which is a little annoying, which is because we're using an approximation algorithm, because greedy is just an approximation algorithm, it's possible that in one iteration, even though sort of the bids have only gotten higher, it's possible we wind up computing an allocation which was worse than the previous one. And we don't want that. Okay, so the approximation guarantee sort of depends on the monotonicity. So the reason I have this old and new is every iteration we're going to be like, okay, let's look at what we just computed with our greedy algorithm. Let's look at what we computed last iteration. And if last iteration is better, okay, let's just use that instead. Okay, so that's a simple optimization, which is you remember last iteration's allocation and you just keep it if it's better than the one you just did. So I'll write that here. If the sum of the bids last time around is higher than the sum of the bids this time around, then, actually let me do this the other way. So what you're sort of hoping is that you've made some progress. And so if that's true, then basically your new tentative allocation is So old is what you're saving the tentative allocation in. Okay, so you compute this new one new, and if that's better than the one you were saving, well then now this better one is the one that you start saving. Okay. So what does it mean to lose in this sort of greedy algorithm step? It means that you're neither in old nor have you dropped out. Okay. So at this point in the auction, if you're in the set old, you're happy. Okay, you're like a tentative winner in this auction. You're tentatively going to get all of the goods S sub I, and the current price for that is going to be BI. If you're not in old at this point, you are not a tentative winner. And those are the ones that are asked to either double their bid or get lost. Okay? And that's it. So that's the auction. And then the final allocation is just the S sub I's, where I is an old. And then the final payments were just the last bid that you ever made. Okay. So let me do a quick example. So let's look at 4 bidders and 4 items, and D equals 2. And let's even just do it for a single-minded example. Okay, so let's say, so these dots are the 4 items, and the 4 bidders I'm going to represent with these circles. Okay, so each bidder is single-minded. It wants a pair of goods. Okay. So let's say bidder 1 is willing to pay 6 for this bundle, willing to pay 5 there, willing to pay 15, willing to pay 12. Is it clear what the example is? So there's 4 bidders, each has exactly 1 bundle, and the bundle consists of 2 goods. And again, remember, the seller, we don't know what these pairs are. We have no idea, okay? So it's unknown. All right, so what's this auction going to do? Well, so initially all the bids are 1. So let's just say we go through the bidders in order of name. Okay, 1, 2, 3, 4, okay? So we get to bidder 1. Its current bid is 1. Its current set S1 is all 4 items. Okay? So what the auction does, it says, hey, bidder number 1, because your set SI is so big, bigger than D, we're going to take a pass unless you want to shrink. Okay? And I mean, in this, so let me just point out. Okay, so from a bidder's perspective, I mean, maybe the single-minded case is a little weird to talk about, right? Because as a bidder, maybe you want to think about the following case, right? So maybe you want to think about the case where D is like 10, and you're a bidder, and unbeknownst to the seller, your unit demand, okay? So all you want is 1 item. You don't care which one. They're identical to you, and you're willing to pay like 5 for just 1 item, okay? But D is like 10, okay? Now, as this auction proceeds, right, sort of, it seems like, okay, at some point, I need to stop going for all 100 items. I need to like focus on 10, because I have no hope of being chosen by the greedy algorithm until my SI is down to 10 items, right? But then there's this really kind of non-trivial decision you have to make, which is like, there's 100 items, I just want 1, I don't care which. And now I gotta tell the seller 10 of them, and the other 90 I become ineligible for. So, intuitively, if you're bidding this auction, what you'd want to do is try to like look at the bidding that people are doing and try to see, what's the least competitive parts of the items, and then kind of say, okay. But you're also like hedging, right? You're like, okay, here are 10 items, and I think I got a good chance of getting one of these 10 for a low price, right? So from a bidder, this is the kind of reasoning you have to do, all right? And it's, there's no obvious optimal way to do that, okay? Now, in the single-minded case, it's maybe kind of a too simple an example, because there's really no reason to hedge. Like, what are you hedging exactly, right? So you may as well just kind of say, oh yeah, sure, I'll shrink to the only bundle I want, okay? But still, let's go through it in this example just to keep it simple. So I'm bidder number 1. At the very first iteration, I'm saying either I'm going to get passed over, or I can shrink to these 2 items. And even here, it's not. I mean, you can make a case either way. I could kind of say like, well, my value is 6. I'm going to be asked to double my bid to 2. That's fine. I could just sort of stick with all 4 goods for now. But let's say bidder 1 just says, sure, I'll shrink. I'll shrink my S sub 1 set to just the 2 that I want. And then this auction is going to say, oh, great. Well, in that case, I'll pick you in the greedy algorithm. Okay? Good. So this is a winner in the first iteration. Let's do this. So now we go to bidder 2, okay? So we go to bidder 2. Currently bidder 2, it's S sub 2 is all 4 items, just like everybody else. And these 2 goods have already been allocated this iteration. And so the auction asks bidder 2, hey, I'm going to take a pass on you unless you shrink to a set of size at most 2, which is disjoint than these ones you've already allocated. Right now, bidder 2 is going to say, hey, yeah, I'm not going to do that, right? Because bidder 2 is only happy if it gets that good, and that item's already been allocated, okay? So bidder 2, it actually is clear what they should do. There's no shrinking that makes sense for bidder number 2. So it's going to say, I'll take a pass. Okay, skip me. Bidder number 3, they ask the same question, do you want to shrink or not? And bidder 3 says, well, I mean, it doesn't have to do this, but one sensible thing would be to say, oh, sure, I'll just shrink to the 2 items I want. That's feasible with respect to the ones you've already allocated. And the auction says, great, we'll pick you with greedy. And then 4 will take a pass. Okay? Yeah.
Why wouldn't bidder 2 just drop out altogether?
Well, because its bid is only 1 and its value is 5. So the one thing to think about, I mean, you're right that sort of like at the end of the day, bidder 2 is going to be hosed probably, but bidder 2 doesn't know everyone else's values.
Oh, I see, just know, yeah.
Yeah, so we want to be as close to DSIC as possible. So hopefully already we're seeing this is definitely not DSIC, right? There's really not a dominant strategy in this game. This is actually kind of a non-trivial game to play as a bidder, okay? So it's something else, all right? We'll see what it is. But certainly, but what's cool is, as a bidder, you only have to reason about your own problems, basically, which are not easy, but you really don't care what other people are doing. And that's very strongly in the spirit of DSIC, having no need to reason about others' behavior. Okay, so that's great. So for all this guy knows, its value is blowing away everyone else's, and it just has to be patient. It's going to get what it wants. Okay? All right, so first iteration, bidder 1 and bidder 3 get allocated. Bidder 2 and bidder 4 take a pass, okay? So that gets us sort of through here. Now here, okay, so there was no old one, so clearly the new one's better. So the bidders that are relevant here are bidders 2 and 4. We ask them to either double or drop out. And in this case, bidders 2 and 4 are happy to double, right? Or we would expect them to double, because their values are much bigger than 2. Now let's go to the next iteration, okay? So now we start from scratch, but the bids have changed, okay? So the ordering on the bidders have changed, right? So now the highest bidder, breaking by name, is going to be bidder number 2, okay? So we ask bidder 2. And bidder 2 hasn't shrunk yet, okay? So it's S sub 2 is all 4 items. So the auction says, we're going to skip you because your S sub 2 is too big, unless you want to shrink. And the second bidder will say, sure, I'll shrink to these top 2 goods. And the auction says, oh, great, we'll pick you in greedy then. All right. Now, again, remember, we're going by bid, so we get to the 4th bidder, and we say to the 4th bidder, hey, do you want to shrink or not? Otherwise, we'll pass on you. And the 4th bidder says, sure, I'll shrink to the bottom 2 goods. Greedy says, great, I'll pick you both. All right. Now, when we get to bidder 1, all the items are gone, so it would be pointless to shrink. You'd have to shrink to the empty set. So 1 gets skipped and 3 gets skipped. Okay. So now, 1 and 3, being the ones that were skipped, are asked to double their bids, and they will presumably say yes. And now everybody's already shrunk. Everybody's shrunk down to the bundle that they want. And so now no one even gets, let's see, so now when we go through the bidders again, we don't even bother to ask bidder 1 to shrink or not. We're just like, look, you fit, we'll just pick you, okay? Bidder 2 conflicts with 1, so 2 does get asked to shrink, but there's no way it's going to give up on that upper left good. So it passes. 3 just gets taken without being asked, and then 4 is going to skip. Okay. And so then 2 and 4 both double. And same thing happens. And then 1 and 3 and double. And then once this cycles back again, so this will be an iteration where 1 and 3 got allocated and 2 and 4 got skipped. 2 and 4 are both going to be asked whether to double or not. And now we expect 2 to drop out, right? Because if it doubled, it would go to 8. And notice the prices you pay if you win are exactly what your final bid was, okay? So at that point, 2 drops out. 4 says, sure, I'll go to 8, no problem, okay? And, right. And so then in the next iteration, this is the high bid. So we go to this guy first. We take bidder 4, and then 1 and 3 are both going to pass. Okay? Because 1 and 3 are blocked by us taking 4 in the first iteration of greedy. And so then 1 is asked to double, and will refuse, presumably, because that would take it to 8. 3 will be asked to double, and it will accept, which will take 3 to 8. And then in the last iteration, again, breaking by name, we ask bidder 3 first, or we just notice that bidder 3 is feasible, so we take it. We ask 4 whether it wants to shrink or not, and it won't. And then we ask 4 whether it wants to double or not, and it won't. Okay, so at the end of the day, the only guy we allocated was V3 in this auction. Okay? Which is certainly not optimal, right? Optimal would be the top and the bottom for 20. Okay? But we're not expecting to be optimal. Okay? But that's what it does. Yeah, Rory.
Why are we doubling every time as opposed to like incrementing? Well, it seems like that's what screwed over bidder 3.
That's an excellent point, yeah. So there's sort of two, it's a good point. So we're losing twice. So one loss is just because greedy, even on the real values, is off by a factor of D. And you're absolutely right, we're sort of picking up another factor of 2 loss because we sort of this discretization error, basically. And if we wanted, we could certainly change that factor 2 to a factor of 1 plus epsilon. We'll see a part in the proof where it would get traded off. But you're absolutely right, 2 is sort of arbitrary here. Absolutely right. Okay? So that's the auction. Everyone get it? Okay. Okay, cool. So the claim is that the auction has a non-trivial welfare guarantee as long as the bidders don't do anything stupid. Okay? And so that's what I want to prove to you over the next few lemmas. But that's the goal. That's the one thing I want to say about this mechanism, basically, about this sort of slight relaxation of DSIC. So any questions before we start the analysis? Okay. All right. Good. So, all right, so let me tell you what I'm going to assume. All right, this is important. So let me tell you what do I mean by the bidders don't do anything sort of obviously stupid. So the analysis of the algorithm will be, of the auction will be assuming that the bidders behave in the following way. So the first 2 are simple. So you'll drop out before your bid exceeds your value. Okay, so in this step, if your bid is already strictly more than half your value, then you're going to say, no, I'll drop out. Okay? And again, this is obviously not, dropping out with this is obviously stupid because if you win, you'll have negative utility. It's dominated by dropping out, which guarantees you 0 utility. And then conversely, won't drop out until BI is greater than VI over 2. Because if BI is VI over 2 or less, why not just double, right? Because you might win. If you win, you'll get non-negative utility, and if you lose, you'll get 0. And then 3 is about, 3 just says, when it's obvious you should shrink. So let me spell that a little bit. So whenever BI is already big, okay, so whenever your bid is such that you will refuse the next doubling, whenever BI is bigger than VI over 2, SI is not feasible in greedy so far, and there exists a feasible TI and SI with TI at most D that I wants. Then I will shrink to such a TI. that sound right? So what we're thinking about is, there's a situation where, you get to this part, shrink or don't shrink. And, right. I guess I should say, I think there's one other twist. No, okay, this is basically what I mean. So when you're asked to shrink or don't shrink, and not shrinking is going to result in you being asked to double your bid, and you being asked to double your bid will result in the bid being more than your value, causing you to drop out. Why not shrink? Okay, that's all I'm saying. All right. So and that's it. That's the three assumptions. Okay, so the paper sort of writes down a formal definition about how reasonable this is, but I mean, in this concrete setting, it's just obvious, right? These are sensible. It's not a dominant strategy, but you don't have to know anything about what other people are doing. All you need to know is sort of your value, and you have to be able to basically solve this problem. Okay, so as a bidder, you have to be able to figure out, given the goods that are left, whether you want any or not, whether one of your bundles is in there. So I view these as, while not DSIC, kind of very pleasingly weak behavioral assumptions. And under just these assumptions, we can say that the auction's output will be good, or pretty good. All right, so here's a lemma that we don't necessarily care about in its own right, but it winds up being kind of really useful for the rest of the analysis. Basically, it just says this thing isn't going to run too many iterations. Okay? So under our behavioral assumptions, the number of iterations, which I'm going to call R, is bounded above by 3 times the log of the maximum valuation. Okay? And so the important thing to notice here is that it's independent of the number of bidders, independent of n, which is, you might have been concerned like, maybe every iteration, only one person doubles, and then n iterations, everybody doubles, and so, n times log Vmax would have been kind of, yeah, of course. Independent of n takes a proof, okay? So it's not that hard. All right, so consider the last bidder to drop out, okay? All right, so one case is that this was a bidder that never shrank. Okay? That's an easy case, right? If you've never shrank, then your set SI is too big to be eligible for the greedy algorithm, so you can't ever win. If you don't win, you're asked to double. Okay? And in Vmax doublings, you're going to drop out because it'll be bigger than what you value. Okay? So then, at most, log base 2 Vmax iterations. So the interesting case is when I has shrunk, okay? So let me give you something that's almost but not quite a proof, and then we'll see it's pretty easy to kind of fix it up to be a real proof. So let's say that SI let's say that, okay, so a couple things. So first of all, if you've ever shrunk, even once in your life, you have to shrink to something that meets the cardinality bound. Okay, so there's really this sort of phase transition, okay? For a while, SI is everything, and you're just totally ineligible for greedy, no matter what. And then there's this phase of your life after you've shrunk at least once, where as long as you don't conflict with anybody, you're eligible for greedy, okay? All right, so SI, because they've shrunk once, it's sort of eligible for greedy, modulo feasibility. So, if this guy dropped out, it had to have lost, so it should be conflicting with someone who was a winner. Call the conflicting person J, okay? All right, so sets, you'll recall, so this is at the end of the algorithm, right? So SI is conflicting with some other bidder J. Okay, their bundles intersect in an item. Now, everyone's bundles are only getting smaller and smaller and smaller as the algorithm proceeds. So 2 bidders whose bundles intersect at the end of the algorithm have been intersecting for the entire course of the algorithm, right? Because they're only bigger in the past. And so what that means, and then if you think about it, right, if they've always intersected every single iteration, only one of them could have won. One of them had to have lost. And if you lose, you're asked to double your bid. So one of these 2 bidders, I or J, has to be doubling the bid every iteration. So within 2 Vmax iterations, someone's had to be asked Vmax times and they'll drop out. Okay? So in particular, I mean, the one that dropped out, I, it happens within Vmax iterations, 2 Vmax iterations. Okay, so there is this sort of corner case, I guess I should mention. So it is actually possible, the way I've phrased this algorithm, that you'll drop out, you will have lost, and you don't actually conflict with anybody who's winning. Okay, it's not very important, but I just want to point out there is a corner case. All right, so how could that have happened? Well, here's when it can't happen, right? Suppose in the last iteration, the allocation that was computed, the new one, was strictly better than the old one, okay? So this bidder I was eligible, so we just computed new using this greedy algorithm, okay? And so if that's the final allocation, and I's a loser, then I was not accepted by this greedy algorithm, okay? And the only reason you don't get accepted by the greedy algorithm, assuming your size is at most D, is because you were blocked by somebody. So that's fine. That's the case we're probably all thinking of. The annoying thing is it is possible that in that last iteration of this auction, you computed something that had worse some of the bids than the previous iteration. So you just threw out that greedy computation at the end, okay? And you took the one from the previous iteration. And then you're tempted to say, oh, but I mean, then this bidder I should have conflicted with someone in that iteration, which was true for the set of goods S sub I it was going after in the previous iteration at that greedy computation, which it may have since shrunk. Okay? So there's this corner case where a bidder might have shrunk its good since it was excluded by some greedy computation at a previous iteration. Right? So it is sort of possible that this fails. But then you kind of do the obvious thing. You just kind of sort of reverse back into the auction. And you kind of say, well, look at the last greedy computation where I was not chosen. It's because it's set at that time was blocked with somebody else at that time. Okay? And so in all iterations prior to that one, this is true. I and J were blocking at all iterations prior to this one, so they were doubling. They were basically taking turns doubling. And then ever since then, it must be the case that the greedy computation from that iteration has just persisted as the best allocation for the remainder of the auction. And I is not in that allocation, so every time that allocation is chosen, it's a loser, and so every iteration after that intersection point, it keeps doubling. Okay? So if you like 2 Vmax up at most, up to the point where I and J conflicted in that greedy computation, and then at most Vmax after that for the doublings when I is excluded because you keep retaining the old greedy allocation. Okay? So let's just say corner case. In fact, if you do this argument more carefully, you still get 2 Vmax, but it's probably a little bit easier to think about as just you separate it into 2 parts. The last time that I conflicted with anybody, and then the sort of final phase where it just keeps not getting chosen because we just keep picking the older greedy allocation. So let's just say corner case might add extra log of Vmax. Okay? But so again, the upshot, and this is important, okay, it's really important that this iteration bound is independent of the number of bidders n. It'd be nice if it didn't even depend on Vmax, but if you look at how this auction works, obviously it's going to depend on Vmax with the doublings. Okay? So that's the point. Okay? So that's a good iteration bound. Okay. So any questions about that? All right. So I think what I'm going to do is I think I'm going to tell you the proof plan for the approximation bound. Then we'll take a break, and then we'll do that proof, and then start talking about Bayes-Nash equilibria. Okay, so let me tell you, okay, so again, what we're going to prove is that under these behavioral assumptions, no matter what players do, the welfare of the final allocation is near optimal. Okay? So we're going to do that in 2 steps. So at the termination of the auction, just remember there are these sets that a bidder's going after, and they keep shrinking, keep shrinking, keep shrinking. S hat I, that's just going to be I's set at the very end of the auction, at the conclusion. Okay, whether you're a winner or a loser, I don't care. That's what you were going after at the end. So I's final set. Now, here's an important thing to point out. Okay, so so it's clear we're going to get some welfare loss just because we're using greedy. So we're expecting a D loss in the approximation. But there's going to be a loss on top of that. And I want to just tell you a little bit about why we should expect that. Okay. So let opt hat be the max welfare that anybody could get when I only gets goods from S hat I. Okay? So opt is just the maximum welfare is just the welfare maximum is the allocation. Okay? So for the real opt, anybody can get any items. Okay? And then you just maximize welfare subject to that. So this is a more constrained optimization problem. So the optimal value is going to be worse, it's going to be smaller. I'm saying no, you don't get to optimize over all allocations, only over those where bidder I only gets items that are in S hat I. And again, we're thinking of like there being 100 goods, and S hat I is only like 10. Okay? So there really is going to be extra welfare loss because of this, basically because of miscoordination problems amongst the bidders. Again, think about this case with 100 items. People only want 1, but they're sort of forced early on in the auction to kind of guess a good set of 10 items that they think they can get one of at a cheap price. So you've got all these different, maybe you've got 100 bidders, okay, and 100 items. So you could just have this perfect matching between the bidders and the items, and it would be awesome. Right? But the bidders don't know this. The bidders are having to just kind of like guess, right? They have like very few clues to go on. So the bidders just kind of guess these sets of 10 items. And then the question is, you have a perfect matching that in addition only gives each of these bidders one of the 10 items that they've funneled in on. Okay? And in general, there won't be. There might be a perfect matching originally, but then once there's all these exclusions from certain bidders getting certain goods, all of a sudden there isn't. And there's going to be a worse optimal allocation. So a key conceptual thing we have to do in this analysis is quantify the welfare loss arising from the bidders just in a totally uncoordinated way, trying to guess, where they're going to be able to get a bundle from. Okay? And so that's exactly what this analysis is going to do. So there's going to be one loss because you're using greedy algorithm, and then a loss because of this restriction. All right, so opt hat is trying to quantify one of these losses. It kind of says, suppose I gave you exponential time and I gave you all the information, but you had to respect people's final sets. How well could you do? We want this to be not too much less than the real opt. Okay? All right, so some more notation. Do I need this yet? Not yet. No. So let me state the lemmas. So lemma 2, under the behavioral assumptions I just erased, the welfare of the shrinking mechanism is at least 2dr times opt hat. So let me remind you what all these are. So D, this is our 10, this is our cardinality bound on bundles. R, that's the number of iterations. So that's log V max. Okay? So intuitively, this is going to come from the greedy algorithm. We're sort of losing the greedy algorithm's worth every single iteration. And then also, this is a smaller number than opt. Okay, that's why it's not a theorem. This is just a lemma. Okay, so this is opt. Under the restriction, people can only get the goods in the items in the sets they were shooting for at the end of the auction. And then lemma 3 quantifies to what extent opt hat is worse, is less than opt. Okay. So under BA, opt hat is at least, I think I need a +1 here. R plus 1 times opt. And again, R is the number of iterations, which is log of Vmax. Okay? So again, as expected, because bidders had to sort of funnel in on a subset of goods, we have less flexibility for the allocation, so we're losing something. Fortunately, the loss is just the iteration count, which we know is reasonably small. And then we do pretty well with respect to this restricted notion of the optimal. Okay, so putting these together, we get that the shrinking mechanism is a 1 over d log Vmax squared approximation. Okay? So if we didn't care about incentives at all, we would not have that. Okay? In the special cases, we could get DSIC, and we could get that. In this multi-minded case, DSIC, as far as I know, no one knows how to get anything. And so here what we're doing is we're losing a bit in the approximation, and we're getting a pretty strong incentive guarantee. And that's, as far as I know, the state of the art for this problem. Okay? So let's take a break now, actually. Let's come back at 3:30, and I'll prove to you lemmas 2 and lemmas 3. And then the last part of the rest of that lecture will be, I think, relatively light. I basically just have to do some Bayes-Nash basics, because we haven't done it yet. So getting ready for Bayes-Nash implementations. So we'll talk a little bit about sort of Bayes-Nash equilibrium, first price auctions, and that kind of thing. Okay? So I'll see you at 3:30 for the proofs of these.